Allora, il primo speaker è Luka Boc Thaler, viene dall'Università di Lubiana ed è postdoc da noi a partire da marzo fino a marzo, quindi. Lavora in dinamica olomorfa in più variabili.
Grazie a tutti. I will continue in English. This is a joint work with Uroš Kuzman from Ljubljana. I will say something about reduced dynamics. So, suppose we have a real-world dynamical system. Mathematics is usually used as a tool to obtain equations which sort of describe the system. And in order to analyze the system, what we usually do is suppress some parameters in such a way that the equations that we obtain are more manageable, because we can rely on many variables and it's hard to compute anything. And from this simplified equations, we derive some results. And of course, in the end, it's important to ask whether these results accurately describe the initial dynamical system. So let's say we will simplify everything and mainly focus, let's say, on dynamics in the plane. And for instance, let's imagine yourself standing in the coordinates, in the origin of the coordinate system, and you have objects in the plane. Suppose your objects start at point T1, point T2, T3, and T4. So we're going to look at discrete dynamics here. And at each point, this is a movement of the object, and at each time, its precise location. So it's x and y coordinate. So if you know precise location for all times, basically you know everything. You can say, you predict what happens. But of course, this is a lot of data. You're usually not able to get precise things. So how we reduce, let's say, what can we say if we get some kind of reduction? And by us, let's say reduction would be, we only see the distance of the object from us. Can we still precisely predict what's going to happen with this object? So instead of getting exact coordinates, we just obtain distance at time 1, distance at time 2, and so on. So is there any problem with this? What can go wrong? So for instance, you have two objects which are different, but they move in such a way that their distance with respect to us is always the same. So from our point of view, we don't distinguish these two objects. So there we have some loss of information in general of the system. So an important question is, so how much information about the regional dynamical system is lost in this way? And we're going to try to say something about this. So for us, our model, so what we study is the following. So objects for us are points or complex numbers, so points in the complex plane, or on the Riemann sphere, basically compactified plane. The movement of objects is modeled by the iteration of a rational function of degree at least 2. So rational function on the complex plane. They extend holomorphically to the Riemann sphere as holomorphic functions. So why we look at the rational functions? Simply because theory of dynamical system there is well developed, and we can actually say something about it, not just wave with our hands. So we have some explicit results that we can use how things move. And why degree 2 or more? Because degree 1 are just Mobius transformation, and we can we can really say what's happening there. It's not interesting from the dynamical point of view. It's nothing going on, really. And the distance from it's measured from the origin, is measured using Fukuyumi's study distance. So it sounds fancy, but just imagine the distance from 0 to point of infinity is 1, and the following fact that 2 points have the same distance if and only if they have the same Euclidean distance to. So basically, I mean, like you saw in the picture before, points on the same circle have the same distance. So you can really think as Euclidean distance. The only thing why we use this is because we need some kind of metric on the whole sphere. We can use the Euclidean metric on the sphere. Okay. So preparation lemma. With Zn, we denote the orbit of initial a given point z, 0, where Zn is defined as an image of nth iterate of R at this point. And clearly, two orbits are the same if the initial values are the same, because you have an infinite sequence, like infinite vector, they have to be the same at each coordinate. So if they agree on the first one, and since this is defined that way, they will be the same, and so if and only if. But what can we say about the distances? So we have the following. There exists an integer such that if orbits have the same distances to the origin for first n times, then they will always have the same distance to the origin. So if you have 2 points, let's say this is the origin, and then you move like this, and they always have the same distance. So this one is the same, this one is the same. If this happens for first n times, then it will always be this case. So what this helps us is basically to study the problem in finite dimensional space, not in the infinite dimensional space, as you will see. And just, this is probably going to be only proof, but since it's quite probably understandable for everybody, it's very simple how you can see this. So these functions are real analytic, defined on a compact real analytic manifold. We define Zn as the intersection of 0 sets of these functions in this space. And clearly we have the following, we obtain this by the decreasing sequence of analytic sets. And since the ring of global analytic functions on compact real analytic manifold has material property, this means that this chain eventually stabilizes and from somewhere on is the same. Okay, so it's a little bit algebraic behind it. So from somewhere on, from some large n on, all the sets are the same, which basically means that, okay, you might have changed something, but from there on, it's okay. So what we obtain this way, we finally obtain a reduction map for us. So for a given point from a complex plane, we map it to the first n distances, where this n is from previous lemma. So z0 goes to the first coordinate distance to 0. The first of the point, and the first iterate, and so on. And we write omega as the image of this, as the image of the sphere under this map. So what we obtain this way is the following commuting diagram. So we have a map R over there, like Russian function. We have these two projections, and this R induces the map Q. So this is well defined exactly because of the lemma before we had. So if we have 2 points that are mapped to the same, they will stay the same under iteration of that. And the Q is defined in the following way. It's basically, you can think of it as a shift map if you would write this as an infinite sequence of distances. So it would be basically a shift map. Okay. So for us, we have now this gives us 2 dynamical systems. The first one is up here, so iterations of rational function, and another one is down there. So let's say you iterate this map on space omega. Of course, if this phi would be an injective map, these two maps would be conjugate to each other. So whatever happens here, and vice versa, because we can just sort of turn the arrow. So this means that we didn't, with this projection, we didn't lose any data. Didn't happen. The problem that we said before doesn't happen. In fact, this is not the case. This is never the case for a rational function. So we always have some data loss. So how can we see this? So phi is never injective. We take, for instance, suppose a critical point is not at the origin for simplicity, and these are just circles centered at the origin. So take a critical point of your rational function and look at its critical value. Take a small circle around the critical value. Its pre-image is going to be almost a circle, but think of it as a circle. Take a point here. Since this is a critical part, it has at least two pre-images. And what you do, you just continuously move this point around the circle, and what happens with these 2 points, they move around like this. So eventually they will line up on the same circle. So you have some kind of picture like this. So they're aligned, and this means that these 2 points are mapped to the same point. Yes. So therefore, they get identified under your map phi. And since you can do this for every circle to sufficiently a small radius, you basically obtain a one-dimensional curve. And this curve get sort of mapped here. So points here, this and this, and all like this, get mapped to one point here. And therefore the distances will always be the same on the iteration. And they get identified. Okay, so now I can sort of state the main theorem that we prove is the following. So for non-exceptional rational function R, the entropy of Q and the downstairs map is the same as entropy of R. So I can explain what means being non-exceptional and what is entropy. Just for now, entropy of rational function is, there was a result that we could compute. It's exactly log of the degree of rational function, and since the degree is more than at least 2, this is never 0. So we have something going on. And in the remaining case for non-exceptional maps, whatever they are for now, the loss of information is just too big so that the entropy of downstairs map is equal to 0. So we lose too much information. You cannot, let's say, deduce this from the reduced dynamical system. And in the remaining time, it might sound a lot, but it's one page for each. It's like we're gonna say something about what entropy is. So for now, it's a non-negative number that measures chaos in the dynamical system. So how chaotic it is. We'll say something about in general results in one-dimensional dynamics of rational functions, which is, we said, it's well developed. We will say what exceptional maps are and what the mirror set is. So these are sort of crucial parts that we use in the proof, which we will not anyhow say anything about it. Okay, so let's say something about entropy so that you get an idea. So we have different notions. We have different types of entropy, and here we look only at 2 that are interested for us. And let's say the first one would be a topological entropy. It measures the exponential growth of the number of distinguishable orbits. We'll see how you can see this. Topological entropy can be computed in many cases, but there are some generalization. But mainly, let's say, have started with a compact space, a compact metric space, and a continuous map. So this is your setting. And for every epsilon and n, you define an n ball centered at x in the following way. Suppose you have your point x and you have its orbit, and then in this ball there are points y whose orbit stays epsilon close for the first n times, basically. So if you have point x, then you have r of x, and so on until r n of x. So in here, in this ball, there are points whose orbit stays in a small neighborhood of r for first n times. And in the next step, they can sort of go apart. And of course, if you increase n, you say you want this orbit to be close, remain close for longer time. So these balls are becoming smaller when you increase n. Okay, so topological entropy is then defined in the following way: as a limit when epsilon goes to 0 of lim sup 1 over n of logarithm of n epsilon. And what this is just the number of the maximum number of disjoint balls and epsilon balls. And you can somehow effectively compute this, what it is. Another entropy that we look is the following: is symmetric entropy. So you start with the measure, which is invariant. So it says what's there. It's a ergodic and probability measure. It's a measure of space that's equal to 1. So then you can define the following function with respect to x: x prime over all epsilon lim inf minus 1 over n log of the measure of the ball that we defined before. So one thing is that one has to note that this function is constant lambda almost everywhere, and measure theoretic entropy is then defined as to be this constant. So okay, these are just two definitions that I had to sort of state, but what's the important fact here is the following variation of principle, which tells you that the relation between these two measures is the following. So topological entropy is the same as a supreme of 4 measured theoretical entropies, where lambda is where supreme is taken over all invariant ergodic measures. So what this gives us, remember from before, we have this semi-conjugate system. This gives us for free the following inequality. So variation principle and stuff. Okay, that's for the entropy part for now. Now the dynamics of one dimension, so dynamics of rational functions. So for 2 set is a f, or holomorphic map of rational function R, let's say, is the largest open set in the Riemann sphere, on which the family of iterates is locally continuous. This means that for every, let's say, family of iterates, every sequence you take, you can find the convergent subsequence. And its complement is then called the Julia set. And important thing is to know that both sets are invariant, so they are mapped to itself by R, and also by the inverse of R. So what are some important facts? The dynamics of the 2 set is stable. It means if you start with an initial point, look at its orbit, okay, it moves around, then if you sort of perturb this initial point, then the orbit of the perturbed value is going to be approximately the same as the previous one. So this is sort of stability. What's nice, we have a complete classification of connected components of this set, which is either, so if you have a invariant component, this is a component that's mapped to itself. So either all points or orbits, when we started with the point, iterated, they all converge to a point inside, contracting case, contracting fixed point. Either all points converge to some point on the boundary, it's a parabolic case, or have some kind of rotation domain, which is either domain which is biholomorphic or conformal to disk or to an annulus, and there your map is just conjugate to rational rotation. So we have sort of a complete picture of invariant, the two components, and then it's finished with the following statement that every two component is pre-periodic. So it can move like this for a while, but then eventually it falls in some kind of periodic cycle. So if you take big enough iterate, your component will be, you can consider this invariant component on the map. So we really have a complete picture. And for Julia set, it's like complete opposite of this. It's very chaotic. So a small change of the initial value makes big changes in the dynamics of the points. It's non-empty, uncountable, and if it has empty, non-empty interior, then it's everything. So just to sort of, the usual manner is to show some pretty pictures of this set, because they are somehow nice and some nice fractals or self-similar. The important fact here is that sort of it's important for us in general. It's very special that the Julia set contains a smooth piece, because remember what we do, we sort of compress. And in our reduction, we compress stuff along the circles. The circles are like smooth curves. And then somehow information, if we want to do, let's say, that's when we lose too much information, we'll see later, is when all Julia set is sort of compressed together. Okay. And the last thing I wanted to say is there exists a unique invariant ergodic probability measure, mu, on the sphere, with the maximal entropy there. And the important fact here is that the support of this measure is exactly equal to Julia set, which somehow gives you a hint that entropy really sees only the chaotic part of the dynamical system. It doesn't care about sort of what happens with a 2 set. It's very nice. The entropy there will be 0. But the value of entropy comes from really this chaotic part, J. So once we have this measure, together with what we have seen before, so this part was from before, if you remember. Since mu is measure maximal entropy, this here we have inequality, and we know exactly how much it is. And this here I denote the push forward of this measure down to omega. We can prove that it's invariant ergodic, therefore it's, since here it takes supremum, it's less or equal to this. And what I want to derive from here is that this is less or equal than this. So our proof in general, what we had to do is prove the inverse statement. And this is what we do. We'll not have one. But this is the main stuff that we had to prove in the inverse statement. So that we have equality. So then all inequality here are basically equalities. Okay. So for the final part, let me say what is to be exceptional. In the following the very explicit example, it's nice and easy to understand. So suppose you have a map Z to D. Just think of it as Z squared. So Z goes to Z squared, let's say. So what this map does, if you write this in polar coordinates, it squares the distance and it doubles the angle. Yeah? So you can imagine you have a unit circle. Everything what's inside the unit circle is going to be contracted when you iterate. It's going to be contracted to the origin because the distance is getting squared and squared and squared. So if this is less than 1, everything will be contracted to a point in the origin. So the dynamics here is sort of predictable and stable. And the same thing is outside the circle. So if you have radius greater than R1, everything will go to infinity. So the chaotic part really is only on this circle, the unit circle. And we can prove that the Julia set is exactly unit circle. So for this map, if we use the terminology from before, and n is from the lemma in the beginning, we can show that n in this case is exactly 0. Why? Because if you start points which are on the same circle anywhere, then their images will have the same distance to the origin again, simply because well, in fact it's a triviality. And in this case, a map Q can explicitly be written down as this. Believe me, that it's true. And this map is a homeomorphism of the unit interval itself. And it's known that such a map, like if it's a homomorphism of the unit interval, then entropy, logical entropy is equal to 0. So we have seen that downstairs the entropy is 0, but upstairs we know that the entropy of this map is logged to 2 because the unit map is 2. So we have lost information, and now you can see why. Because what we do with our map 5 defined before, we compress all the points. We identify all points that whose distance is always the same. And the points here, all the set, it's mapped to a single point. If you go down by 5, this is compressed to a single point. So all the information basically is lost, or it's concentrated in one point, which is sort of a bad thing. So for us, exceptional rational function is the one whose real set is completely contained in some circle set at the origin. Because there, like here, this circle is going to be invariant. Therefore, entire circle is going to be mapped down the stairs to one point. And there we lose all the information. And such maps were sort of classified. We can say which maps or what's the behavior of this kind of maps. And for all the other maps, the theorem holds basically. So we have a complete picture. For the last part, which also plays a crucial role in our study, is the following set. It's a set of mirror points. So these all points for which there exists W that with the following property that phi of Z is a phi of W. So this means that we have 2 points that move always at the same distance with respect to us. What we managed to prove is that this set is semi-analytic. It's either dimension 1 or else it contains an open dense subset of the sphere. We have seen that it is at least dimension 1 from the beginning. Remember where we have a critical point, we found a one-dimensional curve there. So it already contains one-dimensional curve. So it is at least of dimension 1. So I will not prove this, but I will just give 2 examples which are exactly of dimension 1, and the other case have open dense subset. So, for instance, suppose you have a rational function with only real coefficients. Then you know that the following is true. So if you conjugate your map, it's the same as if you evaluate your map at z bar, because the coefficients stay the same if you conjugate. If they are real, they conjugate as the same. So what this means is that z and z bar are mirrored. They're going to get identified under the projection, because they're always going to move the same way because of this. If you look at the distances, if you have RZ, the same as RZ, simply because of this fact. So this tells us that every point, except for points in the, at least those points, except those points in the C without the real line, for which the conjugate does not really exist, they are contained in a mirror set, so they get identified. So this this set contains big set, which is also nice. So what we were not able to prove, basically, that I would suspect that this type of functions, with real coefficients or Russian functions, is its rotationally conjugate to it, and these are the only examples for where this can happen. But for now, I was not that successful to see this. And the last example is the following. Don't be afraid. How does this look like? So this is a map P of Z is I times Z squared. So it has a picture as we've seen before. So points inside the circle, the iterates of these points converge to the origin, and everything outside converges to infinity. And the circle is not itself, and Julia set this circle. The only difference here in map before is we multiply it by I, so the real line doesn't stay fixed. Doesn't map to itself. It also rotates the picture a little bit. You'll see why. And what this map does, it just move this picture out of the origin. So it maps 0 to 1, and it maps -2 to infinity. So the roles of 0 to infinity are played now with points 1 and -2. But the dynamics there is still the same. So let's see. This is basically a picture. So this is your point 1, which before it was point 0, and this is point at infinity. It's now point -2. We just shifted the picture. And this circle is a Julia set. So every point in here, in every point here, everything the iterates converge in here. So if you start with point here, eventually we will fall inside this small circle here. And the same holds for outer part. Every point from here will eventually enter this circle. What this means is that no point here and no point here can be identified under the projection. Why? Because maximal distance here and the minimal distance here are different. So if you have a point, if your point jumps in here, it cannot have the same distance to the origin as a point with ends in here. Or some time. And for us, we said 2 points identified, they always stay the same distance from us. So points from here and here, they cannot be identified. So we can only look at this picture, and then we just want to prove that it's really one-dimensional. It's not, let's say, open event subset here. So how we do this? Let's say we focus ourselves only in this small part here, and we prove that in here you only have one-dimensional curve of sort of points that get identified. And how you can see this? So imagine this. If you really zoom closely, these circles centered in the origin are basically, you can think of them as vertical lines, and they foliate your circle. So basically in your circle these are vertical lines. And this point here corresponds to sort of your point 1. So in our map, if you write the equation down, or if you write the Taylor expansion, your map acting on this set is basically like the one that you had before, like z goes to I times z squared. So what does it mean for 2 points to be identified? So we have, let's say, a line. You have 2 points, and in the image, you want these 2 points to be again mapped on the same vertical line. Yes, but the image of these vertical lines here are like this. So they have only one intersection with the vertical line. So, except in this case, if you take a vertical line through point 1, and this here it gets doubled, so this part gets sort of mapped to itself. This exactly corresponds to the first example that we have around the critical point, because for the map, z goes to z squared, right? If you look in this coordinate, this point is a critical point. So we said that around the critical point we always get some one-dimensional curve. And this one here is exactly the one that we get. And all the other points doesn't have any mirrors, let's say. Okay, I will stop here.
Questions? Remarks? If not, let's thank Luka.